Hello everyone, my name is Sofía Guridi. I am from Aalto University and the lead author of the paper Towards More Sustainable Interactive Textiles, a literature review on the use of biomaterials for electronic textiles. Electronic textiles are attracting increasing research interest as they represent a flexible, conformable platform for wearable and interactive applications. To create them, electronic components like cables are combined with textile materials such as cotton yarns in complex structures. These seamless integrations contribute to new user experiences, but bring challenges regarding the material sources and the life cycle of eTextile products. Considering that we are currently facing a big textile and electronic waste crisis, it is urgent to work on strategies for environmentally conscious design of eTextiles. This topic has been approached by researchers, pointing out the relevance of including circular thinking to, for example, create meaningful products and adopting design principles of repairing, recycling, replacement, and reduction. Particularly in this work, the focus is on the material choices due to the impact they have in many stages of the life cycle. So, for this review, we try to answer if we can use better alternatives to non-renewable, scarce, and sometimes toxic plastics and metals to create more sustainable eTextiles, and how these novel materials can contribute to the field of HCI. To do so, this paper delves into a specific category of materials with great potential for sustainability, biomaterials. By them, we mean materials that are 100% bio-based and capable of complete biodegradation. In addition, in the majority of cases, biomaterials are biocompatible, making them particularly suitable for eTextiles and wearables. In HCI, these materials have been explored in the context of a growing interest for eco-conscious, biodigital interfaces and the motivation for addressing sustainability concerns to create, for example, bioclay 3D prints or bioluminescence algae interfaces. Since the field of eTextiles is interdisciplinary, we look into textile design, HCI, electrical engineering, and material science, for which the keywords were a combination between electronic textiles and bioconcepts. As a result, we found only 33 publications in 19 different outlets, mostly from material science. This publication exemplified the use of 9 different material categories, with a clear predominance of carbon-based ones and just 1 or 2 publications for most of the rest. To analyze the results, we mapped the biomaterials to the eTextile system components they were used for, like sensor or conductive traces, which allow us to see their versatility. Now, I will do a quick review of the found biomaterials and their applications to later share our main insights, but you can of course find greater detail on the paper. To start, carbon-based materials like graphene oxide are electrically conductive, lightweight, and biocompatible in most cases, so they are ideal for eTextiles. They can be used in a wide range of processes like screen printing or deep coating to create conductive textiles or yarns for sensors, antennas, conductive traces, and power sources. Cellulose is an extreme abundant polymer that can come from plants but also from bacteria. It can be used in a variety of processes like 3D printing, casting, or weaving, and it has been used to create bio-based optical textile sensors, power sources, and speculative grown interactive garments. PLA is a thermoplastic commonly used for 3D printing, which origin is fermentation. It has been used to create shape-changing textiles and textiles for skin temperature regulation. Mycelium is a root system of fungi that can grow in desired 3D shapes. It has been used in combination with various electronic components to create sensors, substrates, and cases that can be biodegradable and disassembled. Gelatin is a very versatile protein with high gel strength that can be combined with various materials. For eTextiles, it has been used in the format of foam to create, for example, pressure sensors and temperature sensing face masks. Agar-agar has a similar property to gelatin, but its origin is plants instead of bones. It has mostly been used as a substrate and effector when combined with thermochromic pigments. Chitosan is a natural polymer derived from shells of crustaceans as well as cell walls of fungi. It has antibacterial properties and has been used to create an eco-friendly tribo generator. Escherichia coli is a bacteria present in human bodies. It has humidity-responsive properties, so it has been used to create sweat-responsive wearables. And finally, quasi-solid ionic conductors have been used in combination with flour to create malleable dough for bending sensors. So, from an interaction perspective, as you could see in the examples, most of the publications suggested human biomaterial interactions, where on-body placement was predominant. eTextiles for motion tracking were the most common examples, but they have also been used for garment and accessories. When observing how the materials were used, we detected two main categories. Firstly, some biomaterials were used as a substitute to traditional materials, which enabled traditional interactions. For example, using carbon-based conductive yarns instead of metal conductive yarns to create conductive traces. But secondly, and most interesting, most of the biomaterials have new different properties to those found in commonly used eTextiles, which enable new interactions with smart textile interfaces. For example, agar-agar transparency, the natural feeling of mycelium, and the soft and flexible texture of gelatin introduce interesting tactile interaction possibilities, such as the ability to press or squeeze or establish an intimate connection between a life-like bacterial cellulose and the human body. So, from the analysis in the found literature, we propose some insights that can guide the research for more sustainable eTextiles. To begin with, it is clear that biomaterials for eTextiles are an unexplored field that requires more interdisciplinary collaborations and particularly more knowledge stemming from textile design. And this is important because we see an incredible potential to create fully bio-based eTextile systems. Components made from different materials could be combined in the same systems or go even further and propose monomaterial ones using cellulose, for example. This potential could be further magnified by embracing modularity and disassembling. It is also very interesting to see how biodegradability was one of the most important properties shown by the researchers. Biodegradability is thus becoming an important variable to consider when designing eTextile systems, as it can contribute to a closer loop either by returning to the soil, enabling disassembly or reutilization. In addition, we see how it can open novel interaction possibilities, for example, by exploring textile temporality and unmaking as a design variable. But not everything is so bright, because even though promising, the environmental impact of biomaterials for eTextiles remains unclear. There is still a lack of life cycle assessment studies that include environmental and social factors, so this needs to be addressed in future work. While we get there, we see how do-it-yourself approaches are contributing to these material innovations, enabling low-threshold hands-on work and open-ended processes for interdisciplinary work. These accessible manufacturing processes, together with the particular properties of the biomaterials, can also push forward to amplify the interaction possibilities in terms of scale, placement, and context of use. We know eTextiles are suitable for wearables, but there is plenty to explore in the arts, architecture, or stage design, for example. Finally, to really grasp the potential of these novel materials to create sustainable eTextiles, we need to deepen aesthetic and interpretative understandings of them. Qualitative studies into material development could inspire practitioners and researchers to explore new possibilities, harnessing user experiences and interpretations to craft more meaningful and purpose-driven eTextile products. Since this is still a very undeveloped field, we have the exciting chance to speculate about the future aesthetics of eTextiles. To conclude, biomaterials emerge as catalysts for expanding possibilities within eTextiles, not only through their environmental sustainability, but also through their dynamic and transformative nature, fostering a realm of novel interactive experiences. Thank you.